Hi everyone, my name is Hugo Spizer and I'm currently a joint PhD student between two laboratories, the LGP2 and WCPC. I'm going to present to you the STSM I completed between these two labs thanks to the ActInPak grant. So this STSM was conducted between the LGP2 home and the WCPC host institutions, which are the two labs of my joint PhD. The LGP2 stands for Laboratory of Pulp and Paper Science and Graphic Arts. It is located in Grenoble, France, near the French Alps. The LGP2 activity starts from wood science to converting biomass and functional printing. The laboratory is then considered an expert in biorefinery, multiscale biobased materials, functionalization of surface and printing. On the other hand, WCPC stands for Welsh Centre for Printing and Coating. It is located in Swansea on the south coast of Wales. This lab is today one of the world's leading centers for research and development of printing and coating processes, such as screen printing, flexographic, lithographic printing, autogravure, digital and pad printing. The WCPC focuses currently on three research themes: functional printing, 3D printing, and graphics packaging. During a long period of time working in the LGP2 in France, this STSM grant allowed me to come to Swansea and to initiate some work and trainings on the development of electrochemical printed biosensors. This STSM is relevant to my PhD project called Smart and Safe Packaging. Today, packaging is expected to fulfill more and more requirements, such as being light, being strong, recyclable, biodegradable, etc. And more recently, the potential for the integration of advanced functionalities such as sensing, active functions, and security is being explored. My PhD project focuses on the use of nanocellulose and functional materials and their formulation in order to develop sensors and antibacterial packaging, either by coating or printing processes. The targeted applications are medical and food packaging. This field of the research is still quite new and innovative, as we can see here on this bibliometric studies that shows a booming of the scientific publication on this topic since 2005. Within this framework, this STSM proposes to explore the development of electrochemical printed biosensors that could be adapted to packaging applications. Thanks to this STSM grant, I had the opportunity to initiate this part of my PhD project, and because of an ongoing project in the WCPC, the developed sensors application was focused on antigen sensing. Potentiometric sensors can yet be easily tuned to give different types of response, such as pH, gas concentration, temperature, etc. As we're talking about electrochemical sensors, a bit of background on electrochemistry is needed here. In order to characterize the system, cyclic voltammetry measurements were performed. For the characterization method, a 3-electrodes device is classically used: the working electrode on which the electrochemical reaction occurs, the reference electrode against which the potential of the other electrodes are measured, and the counter electrode which is used to complete the electrical circuit. The 3 electrodes are classically merged in an electrolyte solution composed of a redox couple. A potentiostat then is used to cyclically vary the potential of the system, and the collected current is noted. So this is a classic setup you can see here on the top right-hand corner. The electrolyte, classically iron 2 iron 3 solution, successively undergo oxidation and reduction due to the imposed potential, and the collected current will vary accordingly. Drawing the kind of voltammogram you can see here on the bottom right-hand corner. So this is called cyclic voltammetry, CV. So the shape of the CV curve, and so the electrochemical behavior of the electrolyte, is directly linked to the surface chemistry of the working electrode. In the case of our printing sensor, it's a bit different. You can see here an example of the industrial screen printed electrode on the right. In this commercial product, the 3 electrodes device is printed on substrate which is ceramic. The reference electrode is made of silver, the working electrode of carbon, and the counter electrode is made of platinum. The electrical contacts are made of silver. Only 1 drop of the electrolyte solution is deposited on the electrodes, and the same kind of CV curves are recorded. So I'm now going to give you some results. So firstly, commercial screen printing electrodes were used. There are several steps necessary to prepare the electrodes. The carbon-based raw material of the working electrode is first functionalized in order to enable later the grafting of the antibody. Different functionalization agents were used, displaying functional groups such as amine or carboxylic groups. They are called A, B, and C in the studies because the structure is still confidential. After functionalization, the antibody is then grafted on top of the working electrode. The sensor is now ready for antigen sensing. The prepared sensor was tried against 3 different concentrations of antigen, ranging from 500 nanograms per milliliter to 1000 nanograms per milliliter. For each step, the system is then analyzed using the CV tool that I presented to you before. I took here the example of the functionalization agent B. The change of electrochemical behavior of the surface of the screen printing electrodes can be seen on the graph, especially on the oxygen radiation peak. It serves as a first confirmation of the success of the different steps: the functionalization, the antibody grafting, and the antigen response. From these CV curves, quantitative information can also be extracted. 2 parameters were particularly looked at: the amount of charge exchanged during oxidation, Q, and the resistance at oxidation peak, R. The variations of those parameters are also interesting for concluding on the experiments. On the Q and R graphs, funct refers to after the functionalization step, AB refers to the antibody grafting step, AG500 to after exposure to antigen at 500 nanograms per milliliter, and etc. Based on the Q and R graphs, the different steps seem to be successful, but all 3 samples are saturated for the detection of the antigen, and the sensing of detection limit has to be below 500 nanograms per milliliter. Secondly, 2-layer electrochemical devices were printed in the WCPC on PET substrate, and in order to assess the quality of the screen printed electrode developed in the WCPC, several parameters were measured using white light interferometry: the width, the thicknesses, the roughness of the carbon and silver tracks, and also the roughness of the carbon working electrode. No interruption of the tracks and no hole were seen, and so the prints were concluded to be good enough for the sensing part. The WCPC printed electrochemical sensor were characterized again using CV, and however, due to time issue, it was not possible to proceed with all the process of antibody antigen sensing, and only the untreated device was compared to commercial one. The performance of the raw WCPC sensor design was found to be better than the commercial counterpart, as the charge transfer is higher. Furthermore, it supports the strong placement of the platinum counterpart electrode with a lower cost carbon counterpart. So as a conclusion, this STSM was a great opportunity to initiate trainings and investigate the field of printed sensors. A new functionalization method was proven to be effective on commercial carbon screen printed electrodes, enabling the antibody grafting and the antibody antigen interaction detection, yet further testing are required to fully understand the system. Electrochemical sensor was screen printed and displayed interesting properties, yet more time is necessary to characterize fully their performance. As a perspective, the same principle can be applied to different sensors. For instance, the system can be easily modified in order to work as a pH sensors, which is more relevant to the smart packaging area. And personally, I will be working full-time in the WCPC at the beginning of 2019 with a future plan of action focused on carbon-based nanosensors, from raw materials functionalization to adaptability to real-to-real process. And finally, I would like to thank everyone who helped me around in the lab, and especially Professor David Gethin for the hearty welcome and supervision, and also Dr. Zari Cherani for her patience and dedications. Thanks for your attention.